Okay, so let's finish our introduction to game theory with this last lecture about dynamic games. So I will first introduce to you the basic ideas of dynamic games and then apply the concept we had there to a problem that is pricing in the supply chain. Okay, so we all know that we have this Bach or Stravinsky problem or game in which player 1 has two options, player 2 has two options, and then last time we said when this game is played simultaneously, there are two possible Nash equilibria. So the question now is, what if these two players make decisions sequentially instead of simultaneously? Okay, what if one guy makes decision first and then the other guy makes the decision? We want to know what will they do in equilibrium. That means we want to predict their outcome. And how do their payoffs change? And is it better to be the leader or the follower? Okay, let's move on. So it doesn't matter whether we choose player 1 or 2 to move first. So let's assume player 1 is the first guy who makes the decision. So now instead of a game matrix, it's better for us to use a game tree to describe this game because now we need to specify the order of decision making. So a game tree is something like this, and let's explain what's going on here. So at each internal node, for example, here, here, and here. For these three nodes, the labels who is making the decision here. For example, in the root here is player 1 making the decision. Afterwards is player 2 making the decision. Okay, at each link, for example, a link like this, a link like this, the label shows an available action. For example, here, at least we call it decision node. Player 2 can choose either Bach or Stravinsky. And at each leaf, the numbers shows the payoff. And of course, the first number is the payoff for player 1, and the second number is the payoff for player 2. The game is played from the root to the leaves. For example, here, player 1 first make a decision, either B or S, and then given this action, player 2 observes this action and then make her own decision. Okay, so let's try to solve this problem by finding the optimal strategies for these two guys. So the first question is, what will player 1 do, right? But if you are really player 1, what you will do is to predict how player 2 will respond to your action, right? Because you know everything in this game. So as player 1, you'll first do the following consideration. If I choose B, then player 2 will going to choose B. Let me mark this link. If as player 1, if I choose B, player 2 will choose B because in that case he can get a higher payoff, right? And if I choose S, on the other hand, then player 2 is going to choose S. Like this, because 2 is greater than 0. In any case, player 2 will try to maximize her payoff by making her decision according to my decision. This is how we say this choosing B or S is player 2's best response. Okay, so given this prediction, given this knowledge, player 1 can now make her own decision. He knows that if player 1 choose B, the result will be B and B, and player 1 can get 2 as the outcome. If player 1 choose S, the result will be S, and the player 1 can only get $1. So that means player 1 will choose B as his decision. And certainly this is something based on his prediction on player 2's behavior. An implicit assumption here is that all the players are rational, and that's why player 1 can predict what player 2 will do. Okay, we say an equilibrium outcome is a path going from the root to a leaf. As we mentioned, the possible actions they may choose are highlighted with those thick blue lines, and an equilibrium outcome is a path going from the root to the leaf. And in this case, the only possible outcome is for both of them to play B and B. If player 1 is the first mover, then the result will be unique. There is only one possibility, that is they will go to a symphony of Bach. Okay? Okay, so a simple comparison. When this game is in a static version, there are two pure strategy Nash equilibria. That means there are two possible outcomes, or at least two possible outcomes. But when the game is played in a dynamic setting, and if player 1 is the first mover, there is only one equilibrium outcome in which those two guys will eventually go to Bach's symphony. You may want to verify it by yourself that if player 2 moves first, then they will go to Stravinsky. So the payoff match, the payoffs on the available actions, on the interactions, they are all the same. The only thing that is changed is how this game is played, statically or dynamically, and we can see that the equilibrium behavior will change. Is it always the case? You may want to ask yourself, when I give you a static game, if it is played dynamically, will you always see that different players will make different decisions? That's one question. Also, in the previous situation, being the leader is beneficial. And now the question is it always the case? Okay. Answer the second question with our another example, matching pennies. So we had this matching penny game in lecture 2.2, and player 1 and player 2 are showing each other a head or tail. Okay. And the game, if played dynamically, and player 1 is the first mover, then the game tree is here. Okay. Player 1 choose head or tail, and given that player 2 choose head or tail, if both are choosing head, player 1 getting $1 and player 2 lose the game and pays $1, and so on and so on. So now we want to find the equilibrium outcome. Again, player 1 will predict what player 2 will do. If player 2 sees a head, player 2 is going to choose tail. If player 2 sees a tail, she's going to choose head. Okay? So knowing that, player 1 now is hopeless, because if player 1 chooses head, eventually he will get negative $1. If player 1 chooses tail, he will still get just negative $1. And that means in this game, if you are the first, then you will just be destroyed, or you will be dead, because player 2 can always dominate you by choosing something that is different from you. Okay? In this game, there are multiple possible outcomes. We cannot predict whether player 1 will choose head or tail, because that's the same for him. And in this case, being the leader hurts player 1. Okay? Okay, so let's do a brief summary. What we did in the previous two examples is that there's a leader, there's a follower, and the leader makes her decision by anticipating what the follower will do. Okay? She needs to first pretend herself to be the follower and solve the follower's problem, and given that solve her problem. So in general, when there are multiple stages in a dynamic game, for example, it may be the case that player 1 moves first, and then player 2 moves first, and then player 3 moves at the end. In that case, we will generally analyze those decision problems from the last stage and go backwards to the first stage. We will first solve the last stage problem. And given that last stage behavior in mind, we can solve the second last stage problem. And if there are so many stages, we will then move to the third last stage, the fourth last stage, move backwards until we can solve the first stage problem. Okay? In general, we move backwards until the first stage problem is solved. This solution concept, in which when we are facing a dynamic game, we do things backwards, is called backward induction. Okay, backward induction. This will be the main solution concept we need to use when we have a dynamic game. Okay, so now let's apply backward induction, apply our knowledge there to solve a particular application or pricing in a supply chain. Okay, suppose there is a manufacturer and a retailer in a supply chain. Manufacturer is here, is the upstream, retailer is downstream. Okay, what's the game here? The manufacturer sells the product to the retailer and the retailer sells the product to the consumers, and their decisions are the wholesale price, we call it W, and the retail price R. The manufacturer sets the wholesale price and the retailer sets the retail price. Okay, as a consumer, I only care about the retail price. Okay, I don't care about the wholesale price, and that's because all I can see is the retail price. We assume the demand is a function of R, which is A minus BR, a usual linear decreasing demand function. A and B, they are just known constants. Okay, we assume there is a unit production called C. This is the cost for the manufacturer to get 1 unit of product. Okay, under this setting, each of them wants to maximize her or his own profit. As a retailer, I act to maximize my own profit. As a manufacturer, I do that for myself. No one cares about the other guy. So now we want to solve this game. We want to predict what's going to happen here. For simplicity, let's assume that A and B are just 1 and C is 0 for a while. We're going to use this illustrative example to show you how may we solve this game and to get some intuition there. We also prepared the general case, like general derivations later in these slides. Okay, so now under this simplification, D of R, the demand function is just 1 minus R. Now let's see how may we use backward induction to solve this game. For the retailer, the wholesale price is given, is fixed to R. The manufacturer announces the wholesale price and cannot change anymore. The retailer makes her decision by observing this wholesale price. So what do? The retailer will solve this problem. I'm trying to find a retail price to maximize my profit. This part is my profit margin, and this part is the total quantity I may sell. Okay, quantity times margin. The optimal solution can be found to be W plus 1 divided by 2. Okay, I hope you already feel familiar about how to solve this problem. Ignore this constraint. Show that this problem is maximizing a concave function. First order condition gives you this, and then verify this is satisfying this constraint. Okay, we say this optimal solution is the best response function. Because your optimal solution, the optimal retail price, definitely depends on the wholesale price. When the wholesale price becomes higher, you are going to set a higher retail price. Makes sense. Okay, now let's go back to the manufacturer's problem. The manufacturer can predict the retailer will do what we did. Okay, given her offer W, the retail price will be something like this. We have predicted that the retailer must do so to optimize his own profit. Given that information, manufacturer can know what will be the order quantity given his wholesale price. Okay, the order quantity will exactly be the demand, be the amount that the retailer can sell, and it will be 1 minus the retail price. And given the wholesale price, we know the retail price is just W plus 1 over 2, and that's how we get the order quantity as a function of W is 1 minus W over 2. Okay, knowing about that, the retailer will solve this problem to maximize his own expected profit. I'm going to choose a wholesale price so that I can maximize my profit, which is the multiplication of the first W is my sales margin, okay, because the cost is 0, and then times the quantity I can sell. When I increase W, I know the quantity is going to go down. Okay, so that's the trade-off I'm facing. The optimal solution can be found to be 1/2 in this problem. Okay, now with that 1/2 wholesale price, we can calculate what will be the equilibrium retail price. The resulting retail price will be defined as R star, which is the best response function with W star plugging in. So we plug in W star here, we get 3 over 4. The whole optimal retail price will be 3 over 4. And we can observe one thing. 3 over 4 is greater than 1/2, and 1/2 is the wholesale price. That means the retail price is higher than the wholesale price. This is a common practice called markup. As a retailer, I must, given a wholesale price, I must add something to get my retail price so that I may earn some money. Okay. We may also calculate that the resulting sales volume, the sales quantity, will be calculated like this, and it will be 1 over 4. The retailer will earn this amount on the equilibrium retail price minus the equilibrium wholesale price times the equilibrium sales volume to be 1 over 16. The manufacturer will do almost the same thing. Here C is 0, and W star times D of R star will be 1 over 8. In total, their total profit will be 1 over 16 plus 1 over 8, which goes to 3 divided by 16. Okay, so that's the end of the solving this game. You may want to verify that this can be done in the general setting. We don't need to assume that A is something, B is something, or C is something. They can be left there as just symbols, and you may try to solve this game by yourself to verify that this can be done. Okay, you may find the optimal wholesale price, optimal retail price, and everything follows. You may find that the results here looks very similar to the illustrative case. It's just a difference of a constant multiple. Okay, so that's how we can say that our illustrative problem is general enough, because it is enough for us to deliver all those insights we're going to tell you in the last slides. Okay, so now let's compare the previous decentralized case with the benchmark case of cooperative supply chain. Suppose the two firms now are integrated together, and they want to make their wholesale and retail price decisions together. The question is definitely, is there a way to make both of them better off? Is there a way to make them earn more money? Only if that's possible, they will have the incentive to cooperate. So consider the following proposal. Let's say, how about this? As a manufacturer, please set the wholesale price to be a constant, which is exactly the unit production cost. That means as a manufacturer, do not make any money, and leave all the power to the retailer, for the retailer to set the optimal retail price. Okay. Here we use this superscript FB, not for Facebook, it's for first best. You can show that this is the best retail price these two firms should do. Given that the sales volume will be 1 over 2, the total profit will be the retail price times the total demand, which will be 1 over 4. Okay, and 1 over 4 is larger than 3 over 16. And 3 over 16, if you still have the memory, is the total profit generated under decentralization. Okay, so when these two firms make decisions by themselves, together they earn 3 over 16. To remind you, this is 1 over 8 plus 1 over 16. That's how you get 3 over 16. This is the manufacturer's share, and this is the retailer's share. Okay? Under the second scenario, when they make decisions together, the total profit is here. It's 1 over 4. Okay? So now the question is, we know 1 over 4 is higher than 3 over 16, but is there a way to split the total profit 1 over 4 to make everyone happy? And the result. Now we show you how may we split the total pie to get a win-win situation. Actually, after several examples, you will realize, as long as the total pie becomes larger, there is always a way to make everyone happy. So let's say this is the decentralized case. The manufacturer earns 1/8. The retailer earns 1/16. Okay? And now the total pie is larger. The total pie is 1/4. Okay, so how about this? As manufacturer, you first take these parts away. The retailer also take his parts away. There are something left over. So why don't we, for example, cut it into half? And for this part, bring it to the manufacturer. This part goes to the retailer. That means both of the firms will get more. Okay, and that's why we say this is a win-win situation. Like the cornered example we mentioned in lecture 2.2, here integration again gives you a win-win situation. And actually that will almost always be the case, that if there can be one guy controlling all those decision-making parties, typically that centralization case will be optimal, or will be socially efficient, and typically decentralization will give you some cost. Our job by using game theory is to analyze those situations that integration is not possible. Okay, if integration is not possible, what should firms do, and what should we do to design, for example, contracts or mechanisms to induce those behaviors? We will talk about those concepts more in details starting from the next lecture, starting from next week. So I will just stop here about the introduction of game theory. Thank you.